Hello and good day. I'm Mr. Adamu. I'm here to make a presentation on our paper titled Optimized State Feedback Control of quadratic Active Suspension System based on Linear Matrix Inequalities Algorithm. The presentation goes as outlined. First, we have the introduction, system model description, proposed controller schemes, results and discussion, conclusion, and finally the references will follow. Vehicle suspension system is a very important component. It's a very important component in automotive systems, which improves the performance of passenger ride comfort, road holding capabilities, suspension deflection, and maximum actuator force. Active suspension system is classified into three basic types. We have the active, we have semi-active, and finally the passive system. Among all the three classes, active suspension system is the most preferred, simply because it has the ability to add and remove energy from the system. Recently, researchers all over the world, from the academia and the industry, they focus their attention in carrying out research based on the active suspension system because of its importance in modern automobile systems. Recently, studies in reference 3, for instance, propose an approximate free control technique, whereas in reference 4, a double loop PID controller scheme is proposed. Fuzzy logic control is proposed in reference 5. Researchers in reference 6 look into design of two separate robust controllers, state feedback and output feedback based on H-infinity control strategy. Composite nonlinear feedback control approach is proposed in reference 7. Adaptive feedback control approach is proposed in references 8 and 9, whereas researchers in reference 10 study robust infinite time tracking control. More so, robust adaptive control is proposed in reference 11. An intelligent controller based on fuzzy logic technique is further proposed in reference 12. Adaptive PID sliding mode controller is implemented in reference 1. Output feedback based H-infinity controller is suggested by researchers in reference 2. Linear quadratic regulator LQR and PID control methodologies were presented by researchers in reference 13. More studies in reference 14 considered a non-fragile H-infinity controller. Hybrid control based on PI sliding mode approach is suggested in reference 15. More recently, in reference 16, adaptive backstepping control scheme based on fuzzy logic approach is considered, with sliding mode control considered by researchers in reference 17. Studies in 18 again propose sliding mode control. Neural network predictive controller based on predictive analytics is proposed by researchers in reference 9. A novel technique based on cloud-aided adaptive backstepping method is proposed in reference 20. In this our paper now, an improved state feedback controller using linear matrix inequalities LMI is proposed, and this is compared with linear quadratic regulator LQR using both active and passive suspension systems in order to reduce vehicle body oscillation due to irregular road terrain, or in other words, due to irregular road excitations, which have significant effect on passenger ride comfort at the same time the vehicle stability or the road holding capabilities. Based on simulation studies performed in this our study, the effectiveness of the proposed controllers or the effectiveness of the proposed controller is validated. The system model is shown as in figure 1, which comprises of the hydraulic actuator. The MS stands for the sprung mass, which comprises of the chassis mass of the chassis. MU is the unsprung mass, which comprises of the mass of the wheel assembly. The suspension elements, they are here. FS stands for the spring post. FD, the damper is here, the damping post, whereas the element here is the hydraulic actuator. The FT and FB stands for the tire force, where FB stands for the damping force. The model equations are described as shown in equation 1 and 2, whereas table 1 shows the various parameter values used to carry out the simulation studies. Okay, the table 2 shows the various parameters used in carrying out the simulation studies for the hydraulic actuators model. Okay, the proposed controllers now, the proposed control scheme. Okay, an improved state feedback controller using the LMI is proposed, and this is compared with LQR using both active and passive suspension system in order to reduce the vehicle body oscillation due to irregular road terrain or excitation from the irregular road, which have significant effect on passenger ride comfortability and the vehicle stability. And then simulations we have performed in order to validate the effectiveness of the proposed optimized LQR controller in this regard. An LMI region is a subset of the complex plane, which is presented by an LMI as reported in reference 22. The dynamic system transient performance may be improved by locating its poles in an LMI region. There are different forms of these LMI regions, which include the vertical strip, horizontal strip, circular, and septo, among other shapes. Figure 2, we're going to see the figure presents the LMI region used in this study, which is a combination of the circular and the vertical strip. The circular and the vertical strips. The LMI equations are described or are shown by equation 12, 13, and 14. Then the dynamic system represented by the equation 9 will have all its poles lying in the LMI region shown in figure 2. The LMI in 12 and 13, equation 12 and 13 represents the vertical strip, while the LMI in 14, equation 14, represents the circular centered at C or C, 0 with radius r is greater than 0. Figure 2 is here, the LMI region. We have all for stability, where we have all the poles in the shaded region, and the third figure, figure 3, shows the control system block diagram, where we have the K gain. Thus, the control architecture of the control system involving the proposed controller is shown in figure 3, where X is the state vector, U is the control input, R is the reference input, where K is the controller gain vector, and N is the reference input scaling factor vector. Equation 26, 27, and 28, 29, and 30 show further the LMI equations, and by solving the LMIs in the equation 26 to 29, P and M can be found. The controller gains are obtained by substituting P and M in equation 13 as K equals to the following values, where the K matrix is obtained using a MATLAB program, where we run MATLAB program and we obtain the various K values. Figure 4 shows the schematic of the LQR controller, where we have the K gain. The linear quadratic regulator is a full state feedback controller, which is model dependent. It is an optimal control technique that is very powerful in terms of input tracking, output, and state regulation. References 23 to 25. Figure 4, the same figure 4, shows the schematic of the LQR control systems. Equation 13 shows the performance index of the LQR controller, whereas equation 32 shows the input vector to the controller, which is given by kx, negative kx. Equation 33 further shows the LMI equation, where K is the design matrix gain obtained by tuning the parameters of Q and R matrices, and P is the solution of the Riccati equation given in equation 20 as shown by equation 33. Those solving equations 33, the controller gains were obtained as in the matrix. Now the results now. To verify the effectiveness of the suggested technique, computer simulations were carried out and then performance comparison were made between the LMI and the LQR controllers with respect to the passive suspension system, the quadratic active suspension model described before, and the proposed controllers were simulated using MATLAB simulation environment, and then the characteristic nature of the typical rod input disturbance is given as in the equation, where we have the plot. Figure 5 shows the typical rod importance, typical rod input with two different spikes describing the bumps, where equation 6 shows the results obtained for vehicle body acceleration, the car body acceleration, in which it comprises, or it shows the passive system, the LMI control, and the LQR control, with LMI showing a significant performance or a better performance in that respect. Figure 7 shows the wheel deflection, with the same thing as the first one in figure 6, where figure 8, the suspension travel is also, the result for the suspension travel is also shown, where the LMI performs significantly better. In order to achieve the desired objective of better vehicle suspension system in improving passenger ride comfort and road handling capability, car body acceleration and wheel deflection are the two parameters considered in the simulation studies. For comparison purpose, suspension travel for LQR and LMI controllers are presented in figure 8 for both active and passive systems. The results for the vehicle body acceleration shown in figure 6 demonstrate the effectiveness of the LMI in suppressing the vehicle vibration as compared to LQR and the passive system, which guarantee better passenger ride comfortability. Furthermore, as shown in figure 7, the suggested LMI controller produced minimum wheel deflection. The performances of the controller summarize as in table 3. We are going to see table 3 very soon, using the integral squared error and the mean absolute error performance indexing. The table 3 is here. It shows the performance indices, the various controllers we have, and the integral squared error with their respective values for the integral squared error. At the same time, the switching reduction, mean absolute error in percentage with the respective percentage, where the LMI shows significant improvement in the system. In this conclusion now, in this paper, a comparative analysis of LQR and LMI controllers on the linear quadratic active suspension systems were proposed. MAE and ISE were used as the performance indexes, in which a car body deflection reduction of passive system was obtained as 75.01%, LQR 82.65%, and the LMI 89.11% were recorded using mean absolute error, and the effectiveness of the control schemes was further confirmed by recording small errors using the integral absolute error, which were obtained as for passive 4.11 times 10 to the power minus 6, for LQR 3.24 by 10 to the power minus 6, and finally the LMI controller gives 2.19 by 10 raised to the power minus 6. Simulation studies further prove that the LMI controller performs better in terms of minimizing the car body deflection, effects, and also guarantee better ride comfortability and quality, and better vehicle stability when compared to conventional LQR and the passive suspension system. It was recommended, therefore, that in future an experimental implementation of the proposed technique and other robust control schemes should be considered, should be further explored. And finally, the references. Thank you very much for giving us the opportunity. And before we conclude our video presentation, we would like to give our response to the questions raised by the reviewers. The first question is saying how different types of suspension components affect the control. Are there any calibration problems? The different types of suspension components are basically the mass, the spring, and we have the damper. These components, they form part of the model parameters. The controllers we propose, they are model-dependent controllers. We have model-dependent control, and we have the non-model dependent control. For our research here, our paper studies here, the controller proposed is a model-dependent controller in which the model contains or depends on these parameters, and therefore these parameters, changes in these parameters definitely affect the system control here. And in the implementation of the system, definitely the issue of calibration has to be considered, because this is a very important term, and the calibration problem usually starts with an initial value of the model parameters. That is our response to the first question. And now the second question is saying, in our own view, what is the potential of making the solution more approachable by consumers? That is, or for example, to have users be able to adjust the setting for commotion from an infotainment system. Will it comprise the safety of the implemented solution? Of course, the customers will have a better choice in actually making use of the proposed system, and that simply because the safety issue in the proposed system is not compromised, simply because the system offers more improved comfort and vehicle stability, and at the same time a better ride comfortability by simply reducing the vehicle body oscillation and improving the vehicle stability. Okay, and that the safety will not be compromised. We thank you very much for giving us the opportunity to put down our paper, for our paper to be considered in this respected conference. We look forward to joining the conference in the future. Thank you very much.